Bismillahirrahmanirrahim. Welcome to topic 5.3.3 round robin scheduling algorithm. So before we go further, I would like to take note of mistake that I made in the previous video. At duration 4.24, it is not waiting queue actually, but ready queue. Yeah. Okay, so what is queue? Now we continue with round robin. So round robin, each process get a small unit of CPU time, also known as time quantum, or we represent it as Q. So it is usually between 10 to 100 milliseconds. So after time quantum has elapsed, the process is preempted and added to the end of the ready queue. Okay, so we look at this example. So this set of processes with the CPU burst time in millisecond has a time quantum equal to 4. The arrival time for each of these process is 0. Thus we start with process P1. Okay, after the after this process has exceed the time quantum, the timer will interrupt and preempt this process. So it will release the CPU to the next process, which is P2. So since process P2 is the CPU burst time is less than time quantum, so it will release the CPU voluntarily. Okay, and then continue with the next process in the ready queue, which is P3. Okay, so likewise P3 also release CPU voluntarily. So since P1 still has remaining execution time, so the process, so each process will be continue until the end. So the average waiting time for this example is 17 divided by 3 is equal to 5.66 millisecond. Okay. If there are n processes in the ready queue, okay, and the time quantum is q, then each process get 1 divided by n of the CPU time in chunks of at most q time unit at once. So for example, let's say we have 5 processes, okay, and a time quantum of 20 milliseconds. So each process will get up to 20 milliseconds every 100 milliseconds. Okay, so and no process wait more than n minus q time units. Okay. Right, so timer interrupts every quantum to schedule next process. So only if the CPU burst of the currently running process is more than time quantum. Okay, this statement we already explained in using the example previously. So for the performance of round robin algorithm, depends heavily on the size of time quantum. If the time quantum is extremely large, okay, the round robin policy is same as the first come first serve policy. If the time quantum is extremely small, the round robin approach can result in a large number of context switches. Okay, so very short time quantum should be avoided. Okay, okay, we look at this slide. Okay, time quantum and context switch time. So if assume for example that we have only one process, okay, of time units. So if time quantum is 12 time units, okay, the process finish in less than one time quantum with no overhead. Okay. Right, so for the second example, so if the time quantum is 6 time units, so the process requires two quanta resulting context switch. Okay? So if the time quantum is one time unit, okay, then context switches will occur, okay, showing the execution of the process, slowing the execution of the process accordingly. Thus, we want time quantum to be large with regard to the context switch time. In practice, most modern systems have time quanta ranging from 10 to 100 milliseconds. Okay. Thus, the context switch time is a small fraction of the time quantum. Okay. So, in a conclusion, as a conclusion, although the time quantum should be large compared with the context switch time, it should not be too large. Okay? As we pointed out earlier, if the time quantum is too large, the round-robin scheduling degenerates to an okay, refer to this slide. Okay, if the queue is too large, okay, round-robin scheduling degenerates to an first-come, first-served policy. So a rule of time quantum, a rule of thumb is that 80% of the CPU burst should be shorter than the time quantum. Okay, so so that the context switch is less than 10 okay, sorry. A rule of thumb is that 80% of the CPU burst should be shorter than the time quantum. Okay, so we look at this slide. Okay, turnaround time also depends on the size of time quantum. As we can see from this figure, the average turnaround time of a set of processes does not necessarily improve as the time quantum increase. In general, the average turnaround time can be improved if most processes finish their next CPU in a single time quantum. Okay, the example is given in the textbook, so you can refer to the textbook. Right, so that's all for the round-robin scheduling. Thank you for watching.